You'll be fine. I guess I could offer it if anybody wanted to take one for a formal grade. You could take it. I'd be willing to do an optional one. I think. I don't know if that would.
Yeah.
If it was optional, would you take it?
I don't know, because then
Oh,
I missed
wow.
What?
This is not, oh, he's got a popcorn maker. Whoa. That is so cool. Ah, she's awesome.
You like her?
I've only interacted with her a few times and it's been great. And you walk by our classroom and kids are sitting there actually doing work in junior high and you're like, whoa, whoa, and they're sitting there. She's actually like walking around helping students unlike me. I've often thought, whoa, she's real. So,
She's doing her job.
she's doing her job, yeah. I imagine in junior high you need to do that a little bit more. I do that with the freshmen a little bit. I walk around and
You do?
yeah, a little bit more. You know, keep them on task or help them a little bit. So, okay, so we let's get into 20-3. There's only 11 problems on here. However, they're story problems, so traditionally they might prove a little bit more challenging. With this, with that being said, the goal of working with these or doing these is that we will use our knowledge that we are gaining from our concepts of calculus, which is what we're doing right now, and then with that knowledge of calculus, we will apply that to these story problems. So in that, there might be some other methods possibly to look at it, but we'll be required to utilize the concept of derivatives and things like that. I think of one probably, actually. So let's go ahead and take a look, or let me just describe for us. When we were talking yesterday about graphs, you have some sort of graph and it comes out like this and something like this. Okay, there's a cubic graph. What we know in this cubic graph is we see that we would have a maximum and we would have a minimum. Those are called local maxes and mins. And in that, we know that at the maximum value, the derivative, right, or the slope of the tangent line, same thing, is equal to 0. And then what is the derivative here? 0. So what our goal is we're going to talk about maximum problems and minimum problems. So what's the maximum volume of something? So, or what's the minimum cost on something, or maximum profit on something? And our goal will be to write equations, and then to use the concept of the derivative with the equation, say, hey, to maximize my profit, I'm going to find out where I have a maximum, and the way I find out I have a maximum is to find the derivative, and then find where the derivative is equal to 0. And then do it that way. So we're taking what we did yesterday, talking about the maxes and mins, and then applying it to like some story problems. So that's what we're doing. So not any new calculus, just working with story problems, setting up the equations for that. So let's go ahead and take a look at some of your problems. Will be the easiest. I don't have extra problems that I have typed up for you to do for examples. So this will be nice. We'll just do some of your homework problems. So go ahead and page 772, and let's take a look at number 1. Okay, so again, our goal is to work with the calculus on this stuff and with the derivative. And so that's like on the test, you may say, oh, I graphed it and I found the max that way. Well, we're going to have to use the derivative and some concepts of that. So let's take a look at number 1. It says the base of the rectangle is on the x-axis and the upper 2 vertices are on the parabola y equals 3 minus x squared. Okay, so they have this picture, and they have the function y equals 3 minus x squared is the name of the graph, so we know that's up 3 like that, and then hits maximum there and comes down like that, and then that didn't look very good, but something like that. Okay, Then they have this box inside, like this, like that, and then this is x comma y like that. Okay, so far we know the base of a rectangle is on the x-axis, okay? Check, here's our base of the rectangle. And now my picture is not quite symmetrical like theirs is. The picture should be symmetrical. Symmetrical meaning the distance from here to the origin and the origin out to here should be the same. Okay. So then it says the upper two vertices are on the parabola. So this vertex will be on the parabola, this vertex will be on the parabola. One thing to make a note of is that if this is over x up y, this one over here, how would we describe it in terms of x and y?
Negative x.
Yeah, negative x comma y, where x is the same value, just positive and negative. Yep. So then it says, show that the area of the rectangle a of x equals 6x minus 2x cubed for all values x is greater than 0. Okay, so what they're telling you is, they tell you this is my area. My area is 6x minus, right, 2x cubed. So when they say show, what they want you to do is to write an area formula and then end up there. So we already know what the area is, we want to write a formula, or how do we get there? So when we do that, what we can recognize is that if we picked a point like, okay, so we have x, y there, what would this point be right there? If this is x, y, what would this point be? X0. And what would that point be?
Negative x0.
Negative x0, right? And so, now with that, why are we looking at that? Well, to find the area of a rectangle, what's the area of a rectangle?
Base times height.
Base times height, right? And so we look at this rectangle and say, okay, base times height, right? And so we can think of the height, we could say the height is y, right? But the other thing we know is what's the height, because when we look at the area doesn't have, you know, something times y, they have only x's. So what do I know my height is?
3 minus x squared.
Yeah, the y value is 3 minus x squared. So when we think about the area, we're going to say area is equal to base times height. That's great. We know that we want to function all in terms of x because it's a of x equals something. So we could write this as a of x is fine, and what we need to do is represent the base in terms of x and the height in terms of x. Well, we just represented the height in terms of x. You just told me it's 3 minus x squared because that's my y value, which is y equals 3 minus x squared. And then my base, if I look at the picture, and that was, I kind of jumped to marking those points rather than discussing base times height first and then marking the points. But if I look at the base, what's the distance of the base?
2x.
Yeah, 2x, right? Now where do you get 2x from?
Because it's x out from the origin and x back from the origin.
Yeah, and so even though we're going in a negative direction when we talk about the length of that, we would say the distance from here to here is going to be 2x. Or that's fine to say negative x here. The distance is going to be x minus a negative, x minus a negative x. So x plus x, therefore yes, 2x. So what I know is the base is 2x. And then I say, okay, it's equal to, distribute that in, 6x minus 2x cubed, okay? So then we say, hey, we've shown how we got there. So that's how you would show something like that. And if there was a problem like that on the test, you could do, mark up the picture, show like, hey, y equals 3 minus x cubed, something like this, right, would work to show that. Or you could even, probably let you just go like this and show that that's where we came up with that. Okay, so A is done. We're showing that the rectangle is that. Then B, it says show the rectangle as the greatest area when x is equal to 1. So again, this is what I talked about at the very beginning, is when we talk about the greatest area or the least of something, we want to find out for a graph, right? For a graph, Now that's a cubic graph, which is what we're dealing with. But you could have a problem that has a parabola, the same concept. What we're looking for is, okay, where is my tangent line equal to 0, meaning where is the derivative equal to 0, where will give us a max, right? So how do I find out with calculus where this occurs? And we actually did these back in chapter, I don't know what chapter, but what we did is we would actually take this and then put it on a graphing calculator and find the max value. Here, our goal is to take the derivative, right? So a prime of x. So we're going to do the derivative of a, and then we're going to write, what's the derivative of a?
6 minus 6x squared.
6x squared, right?
Instead of
And
equal
then,
to 0.
now in this case, they already told you the greatest area occurs when x equals 1. They already told you that. But you're just confirming that by stating, okay, that's equal to this. Set the derivative equal to 0, which gives us our tangent line, right? And then you can factor, however you want to solve it, you can factor out the 6 or just divide the 6 over, however you want to solve it. You get x squared is equal to 1, and therefore x is equal to plus or minus 1. Therefore, we have shown that the greatest area occurs at x equals 1, like that. Okay?
Wait, what? How did you didn't,
How did I go where?
from a prime of x to, I understand why you put 0, but I don't understand the equation on the right.
Oh, this one? Well, to get from here to here?
No, I understand that.
Oh,
Okay.
here I just factored out a 6,
Oh,
which is kind of funny to factor out a 6. I don't know why I factored out a 6, because normally I wouldn't.
yeah.
No, unless it was a variable, then I'd factor out the variable, but I factor out 6. So yeah, it is another easy way to solve it. 0 equals is just add the 6x squared over,
Okay,
and then divide both sides by 6, and then do that.
okay.
Yeah. So then now we've proven or shown that yes, the maximum area occurs, excuse me, at x equals 1. I don't know. Yeah, we're good there. I was just wondering yesterday. I don't know if they talked about this, or if they want us to talk about this here. Okay. Yeah, I should reference this here. What we've done is correct. We're good there. One thing to make a note of though is on this problem. Let me do a graph of this problem. If we were to graph out the area formula, we know that the area is going to be positive, right? And so if we took the area formula and we said, okay, this is my area formula. What I would know is that if I were to graph this, you can graph it on your calculator, or also recognize that you have an x just for my original area, not my derivative, but the original area, x is equal to 0 there, right? And then the other zeros would be plus or minus root 3. So your graph would be plus or minus root 3, so this is over 1, over 2, root 3 occurs there, and then negative 1, negative 2, root 3 occurs there. So we know my graph is going to have those x-intercepts. What then we do know is that area has to be positive. So when I go to graph this, if my graph looked like this, without actually doing without plugging it into the calculator, or without doing a sign analysis, sign analysis, it's a positive and negative, right? If we looked at this graph, we would state to help us understand, this X represents what you're plugging in, right, for here to get the base of the rectangle. And then the output for this function is, what is my Y value that I'm outputting? So if I show it this way, what I see is that what we're stating is that if you plug in a negative X, you would end up with a positive area right there. If you plugged in an X value between 0 and √3, this is √3, again, we got the √3 from right here, you would be stating that you would be getting out a negative area value. But what we just saw is we said, hey, when you plug in 1, this is showing that this should be a positive area, right? Because it's giving us a max. So based off of that knowledge, just kind of talking about that, I would know that this graph is incorrect. Meaning, it should come down like this, up like this, and then down like that. That's what we should have. Okay? So anything between 0 and √3 will yield a positive area. After that, if you plugged in 5, let's say, what you would realize is that you're going to get out like a negative area, which is impossible. Now the reason why it's possible is that if you were plugging in 5, your X value right here, this would be plugging in a value out here, and then it would be reversing my rectangle, you know, the endpoint would be there. Your rectangle would fall outside of the parabola, so it no longer fits in the parabola. So all of your rectangle shape is going to occur in here. Now it could be moved down there, and so it's a skinnier rectangle, or it could be moved up here, and it'd be a skinny rectangle this direction, right? Something, but it's all going to occur up here, meaning between √3 and negative √3 in there. So my point of showing this though is for us to consider, we found that we had a derivative equal to 0 at plus or minus 1, which tells us is that this graph looks accurate. At -1 I'd have a minimum, at +1 I have a maximum. One thing to consider though is that for our domain of this actual area function is that we would erase here and we would erase there and state, this isn't a parabola because it's part of a cubic curve, even though it kind of looks like a parabola. But that's the only actual part of the graph I'm looking at, meaning my domain is x is greater than 0 or equal, I can't equal 0 because then it'd be nothing, less than √3, okay? So that's my domain, it has to be greater than 0, less than √3. So the reason why I'm bringing this up is that when we talk about maxes and mins, yesterday we talked about, you know, absolute max and then global or local max, is that we must consider endpoints as part of the process as well. So those also could be our extreme values. Meaning, if we look at our domain, these both yield the minimum value, this is going to yield the maximum value. So we have to also look at endpoints when considering domain. And so if you had another graph, let's say that looked like this, and we went like this, okay, then you may have a maximum value. This would be a local max, this would be a local min, but then our global actually may be here. Versus yesterday we were showing graphs that just kept going to negative infinity, so it's like, yeah, it's a negative infinite value. But what if it actually ends here? Then this value could come into play as that's actually a minimum value that we yield based off of our domain of what we're looking at. So if there is a domain restriction, we should consider the endpoints. Here, based off of this, we actually can look and say, well, the endpoints are not going to yield the maximum area. And so therefore the endpoints are minimums, but they're not the maximum that we're worried about. So endpoints can matter. They do matter if they come into play for us, depending on the problem that we're looking at. So let's take a look at let's do like a manufacturing one, number 5. Jump up to number 5. Manufacturing, congruent squares are cut for the corners of a rectangular sheet metal. So if you look at this one, on number 5, you can see now example 6 is, the picture there is for example 6, I believe. Okay. So let's go ahead and we'll maybe need to draw our own picture here for number 5. So it says, okay, congruent squares are cut from the corners of a rectangular sheet of metal that is 8 centimeters wide and 15 centimeters long. The edges are then turned up to make an open box. So in this case, the picture there they have is for a closed top box. Here, for number 5, we're going to take a rectangular piece of sheet metal. They tell you the dimensions, right? What is it, 8 by 15. Okay, so it's an 8 by 15. You are going to cut out congruent squares in the corner. Okay, and with that then, you are going to if you cut those out, then you would make a open top box. So you cut these sections out. Now it doesn't tell you how much to cut out, it just says cut out something. So if they don't tell you, then they assign a variable, okay? If they don't tell you, the variable they're gonna end up using is x. So you cut out x here, x there, because it's a square. X here, this is a square, x, 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 and x. So you cut out x's out of all that, okay? So then you would, essentially, right, what's going to happen is you'd fold on the dotted line, so that's gone, right? And then you would fold this edge up, that edge up, and then this edge up, and you just make a box out of that. Okay, so it says express the volume of the box as a function of x. So volume, remember what volume is. What's the formula for volume of a box?
Base times height times.
Yeah, base times height times width, right? Or length times width times height, right? So, all right, so we want, it says express the volume of the box as a function, or let x be the length to cut out. So they did tell us express v of the box as a function of x. So express v as a function of x. So it will be v of x. That notation or terminology is important to understand. So v of x equals something for volume, which means I need my base, my height, my width, or my length, all in terms of x.
So 15 minus 2x.
Okay, 15 minus 2x, and we get that from stating here's 15, right? But then you got rid of an x and rid of an x, so 15 minus 2x. So that's your length, or maybe you want to consider that your base, I guess, I'm not sure, however you want to think of it.
8 minus 2x.
And then, yep, 8 minus 2x, that gives us that length there, get rid of the 2 x's, and then x is my height, right? So whatever x is, that's going to be the height of the box. So there you go, there's your volume. We've got a cubic equation, okay? Now it says, what value of x maximizes the volume, okay? So when we look at this, this is, again, when we talk about maximum and mins in this section, we need to find the derivative. Is this in a format that we've been working with to find derivatives? No, because what's the issue? They have what in between these ones? Multiplication, yeah. So for our purposes, and even if this was in calculus with other tools that we have, like the product rule, I would not do product rule. I would just distribute and FOIL this all together. Otherwise, it would just be, it would end up being cumbersome. So let's FOIL this all together and then distribute the x in however route you want to go. And let's see what we get. I'll do it as well. double check, confirm that I did it correct. If I'm wrong, that's fine.
That's what I wrote.
So you got Ruger?
Yep.
Okay, so that tells us the volume. Now, if we were to, again, we've already done problems like this. Do you remember doing these?
Yep.
Something like it. What we did here is we said there's our volume weight function, and then we're going to graph it and look for the max volume or the minimum volume. Okay, so we could do that. Our goal though is to use calculus, use our derivative to find where we have a max and a min. Now, if we were to graph this volume function though, without a calculator, where could we easily find the x-intercepts of this volume function without a calculator? Not derivative, we're not doing derivative yet, but could I easily find the x-intercepts?
Distributing or taking out of x.
Yeah, just right here.
Oh.
Don't make it hard. Yes, take out the x, then factor. Yeah, already done for us. So here we go. What are my x-intercepts? Start with an easy one. 0, we know it goes there. 4. So 1, 2, 3, 4.
And 7.5.
7.5, right? 4, 5, 6, 7. Okay. So we know it's a cubic equation. Without even doing a sign analysis, you know, if I said the graph, does it look like this? That's one option, right? It could look like this. What that tells you is positive volume, because this is a volume function, so your output, so you plug in an x, which is what you're cutting out, you're outputting the volume. Positive volumes occur where you cut out negative x values. Is that possible to cut out a negative x value? No. So we're going to immediately disregard anything up there. Okay. And now, I don't know if this is, I mean, I do know if this is right or wrong, but we're just trying to do an analysis. What it states here is between 0 and 4, if you cut out 0, x, so you don't cut anything out, your volume is 0, which would make sense because it's just the flat piece of cardboard. If you cut out 4, it's also going to be 0, because 8 minus 4 minus 4 is going to be 0, so there is no volume. So this states that anything in between that, you're ending up with a negative volume. That doesn't make sense, right? Because then here, if you cut out 5, it's saying you get a positive volume. That doesn't make any sense because 5 and 5 would be 10. You only have 8 to work with. So we also should know based off of that it's a positive x cubed that it actually opens down then up, you know, if you recall some of that work that we've done before. But trying to, you know, so for us, so we said, okay, great, we've actually just analyzed that is incorrect, the picture that I had, and then we're going to go like this, and then that is correct. Okay. So here, okay, that picture is correct. So what's my domain of this function?
Greater than 0, less than 4.
Less than 4? Yep. So it's got to be greater than 0, it's got to be less than 4. So that's my domain. So in this case, the endpoints actually don't work because if you plug in 0 or 4, you get out nothing. So those ones don't work. You could plug in like, you know, 0.00001 or whatever, but we are looking for the volume is maximized anyways, right? So we're looking for this spot right here. We know though the rest of the graph, I will find when I do the derivative and solve, I'm going to find 2 values. Only one of them is going to work for us, and that's the value between 0 and 4. So how do I find that value? You take the derivative, set it equal to 0, and solve. Now this works to do the derivative because every time you do the derivative, you're reducing your exponents by 1. So you're starting with a cubic, going to reduce it to a squared, and then you can solve with algebraic methods. So what would v prime of x be? V prime of x is?
12x squared minus 92x plus 120. 92 could be wrong.
Oh, okay, I see. 12x squared. Sure, let's put the x squared first.
Oh, sorry, I flipped it around.
No, that's good. 92x and then plus 120.
Yeah.
Okay, and then the nice thing is everything is not divisible by 12.
Nope, it would be 98.
Yeah, but it is divisible by something. So
6 maybe?
no, not 6. 4. I like 4.
Yeah, 4 words. Wait, how's it 10?
Should be 12, right? Or 30?
30,
Right,
yeah.
I'm way off. 30. Should be 10. You go to 30. I don't know if it's factorable. But thanks for catching that error, because with 10 it wasn't going to work.
Wait,
Yeah.
10.
It is factorable.
Yes.
Let's do this 6 and 5,
6 and 5.
maybe.
I like that. 18 and 5 is 23.
Yes, wait.
So we get what, 5/3 and 6? But we know 6 isn't in our domain, so then 5/3 is our answer. And we check that and it says what value of x? 5/3. Great.
Wow.
Wow, we've done it.
It was a journey.
It was a journey. Now it's interesting, they have in their domain, in their answer there, they actually say this and this is equal to 0. But the issue is that if you plug in 0, like we've discussed, you don't get any volume. But you don't get out a negative volume, you just get no volume. So I don't know, depending on the problem, I'm not going to nitpick on something like this. I would argue that it has to be greater than 0 to create a volume and essentially write a volume function. Although a volume could be 0, you just don't have a volume. But a volume couldn't ever be negative.
Right.
But if it's a volume of 0, is it a volume? I don't know. So either it's a book error or a little bit difference in mathematical mindset. So.
And the equation for the volume was 4x cubed minus 46x squared plus 120x. Yeah.
4x squared.
Or 4x cubed, sorry.
Yeah. Right here.
Yeah.
Yeah, 4x cubed, negative 46x squared, and 120x. Okay, let's stop there. We may need to, you guys can start working. These can definitely be a little bit challenging on setting some of them up, but we can work with, help you understand them. So next week on Tuesday, I think I had given us another day to maybe work on these possibly. And then Wednesday, I'm thinking we're gonna aim for the test on, I'd like to take the test Thursday, but to give like a little bit of time.
Test it.
And then you can get your test back on Friday to see how you did.
And then the final will be
So
Tuesday.
the final will be Tuesday. So I think what period is this?
Third.
So
How many test grades is the final word?
2.
2. Oh.
But reasonable chance